Today we will be talking about the LLL Lattice Basis Reduction Algorithm. This takes a basis for your lattice and turns it into another basis with some desirable properties. To get a feel for the cadence of this algorithm, we'll go through some worked examples in both 2 and 3 dimensions, and then we'll jump into some applications. There are loads of applications for this algorithm. These are just some of the ones that I found most interesting. The biggest takeaway of the LLL algorithm is that you can get a basis for your lattice that is reasonably short and reasonably orthogonal in ways that we will make precise later. Suppose you were handed a lattice L with a basis B0 through Bn. For convenience, we phrase everything in the language of Zn plus 1. However, you can apply this algorithm to any lattice. For instance, if you're applying this in the world of algebraic number theory, you may wish to do this to an ideal of the rings of integers of a particular number field. The algorithm here will take our input basis and gradually augment it until we converge to a basis that is reasonably short and reasonably orthogonal. We then calculate the Gram-Schmidt vectors B0 star through Bn star. We also keep track of the coefficients that show up throughout the Gram-Schmidt orthogonalization process. These are the projections of the basis onto the subspaces spanned by the Gram-Schmidt basis. We also keep track of the index k of our current working vector. As I said before, we take our input basis and gradually augment this until we get our desired basis. We do this by building up a provisional basis element by element, and the number k is such that any index less than k is part of our provisional basis. If we looked at the index k plus 1, this is not yet part of our provisional basis. We have now established all of the variables that we need to keep track of throughout this process. We initialize k at the value 1, and we keep looping until k is greater than n. That is to say, we keep looping until we have a full rank provisional basis. We then loop over all values less than k, and we check a certain size condition based on the indices k and j. If the working vector does not satisfy this size condition, we update the working vector bk by subtracting off the rounded Gram-Schmidt coefficient mu kj multiplied by the basis vector bj. Then we update our Gram-Schmidt parameters. We have changed our basis b0 through bn, so we must likewise update the Gram-Schmidt basis b0 star through bn star and each of the mu ij's. We will perform this process anytime we augment our basis because we want the most up-to-date information on our Gram-Schmidt parameters. We then check the Lovasz condition named after mathematician Laszlo Lovasz. If this condition is met, we increment k, but if the Lovasz condition has not been met, we swap the working vector with the previous index, we update our Gram-Schmidt parameters once again, and we set k equal to the max of k minus 1 and 1. Once this process terminates and k finally becomes a value greater than n, we simply return the basis vectors b0 through bn as our reduced basis, and these will have the desired properties that I keep alluding to. Perhaps the most stunning and important property of the LLL algorithm is that all of this happens in polynomial time. That is, for a computer, all of these operations happen relatively fast. This is what opens the door to all of the powerful applications of this algorithm. Further, there were no hypotheses on L, so we may apply this algorithm to any lattice. What we have just done is produced what is called an LLL reduced basis. This is a basis that satisfies the size condition and the Lovasz condition. What the size condition says is that the magnitude of each mu ij does not exceed 0.5. What this buys us is a guarantee that the outputted basis is length reduced. The Lovasz condition is a little bit harder to state, so I won't bother reading it out loud for you. It's also a little bit hard to say intuitively what this should do to our basis. However, I've seen Jeff Suzuki at Brooklyn College explain this in a very good way. He says that the Lovasz condition says roughly that the current working vector is big enough to be our next provisional basis vector. When looking at the inequality for the Lovasz condition, you may be wondering, well, where does the quantity 3/4 come from? And it turns out that this choice is a little bit arbitrary. In fact, if this is a parameter delta that lies within the interval 1/4 to 1, we are guaranteed to get an LLL reduced basis via this algorithm. However, it is just convention that we take delta to be 3/4. What the size condition buys us is a bound on the first vector in our reduced basis based on the covolume of the lattice. This also happens to be the shortest vector in our reduced basis. Note this is not the shortest vector in our lattice L. Finding the shortest vector in L is an NP-hard problem. A polynomial time algorithm like the LLL algorithm cannot solve an NP-hard problem unless P is equal to NP, which it's probably not. Rather, the LLL algorithm has a decent chance of solving the approximate shortest vector problem, which is finding the shortest vector within some fudge factor. The inequality you see on your screen here is likely different than what you would find if you were to Google about this algorithm, and this is because the basis here is 0 indexed and not 1 indexed. We also have that our reduced basis is nearly orthogonal. This feature is crucial in many of the applications of the algorithm. Just as it can solve the shortest vector problem within a fudge factor, it can also solve what is called the closest vector problem within a fudge factor. This involves finding the closest vector in the lattice to a given point in space. We will now step through two examples of the algorithm in practice, once in a two-dimensional case and another in a three-dimensional case. Here we are given the basis for a two-dimensional lattice, and if we heuristically analyze this basis, we can say it's kind of bad because these basis vectors are pretty long and they point roughly in the same direction, which is typically not desirable as a basis for your lattice. We also compute the initial Gram-Schmidt vectors and begin the process of going through the algorithm. Here the index of the initial working vector k is initialized at 1, then we begin the process of checking the size and Lovasz conditions. We first check the size condition, and we find that mu10 has a magnitude of 2.13. This does not satisfy the size condition, so we must appropriately update the vector b1. We take our previous value of b1 and subtract off the rounded Gram-Schmidt coefficient multiplied by b0. Substituting in the appropriate quantities, we find that the new b1 should be equal to 130. We then go on to check the Lovasz condition, which is likewise not satisfied. We then prepare to swap our working vector with the previous basis vector, and we set k equal to a max of k minus 1 and 1. Because we have just updated our basis, we must now recompute the Gram-Schmidt parameters. Even though k remains unchanged, this has completed one pass through the outermost while loop on our algorithm. On the next pass through this while loop, we again check the size condition, and we find that the magnitude of mu10 is 7.21, and this is not bounded by a half, so the size condition is again not satisfied, so we must update the vector b1. We again subtract off the rounded Gram-Schmidt coefficient times b0 from b1, and we find that numerically the new value for b1 is 45. We again check the Lovasz condition, and we find this time that the Lovasz condition is indeed satisfied. From here, we simply increment k, which gives us two basis vectors in our provisional basis in a two-dimensional space, so we are done. Let us compare the outputted reduced basis to the initial basis we had for our lattice. The reduced basis is a marked improvement on the original basis, being both more orthogonal and shorter. The two-dimensional case is a little bit boring because we can only increment k once before we are finished. This three-dimensional case will be a richer example of how the algorithm will play out. Even though I think this will be a more instructive example than the 2D case, this is a long example and might seem kind of boring if you're already happy with the 2D example, so I've included a timestamp to the next part of the video. Again, we begin by initializing the Gram-Schmidt vectors appropriately and setting k is equal to 1. First, we check the size condition, and we find that the magnitude of mu10 is in fact bounded by 1/2. Because the size condition is satisfied in this case, we need not update any vectors, and we move forward. We even find that the first instance of the Lovasz condition is satisfied, so we increment k. Our working vector now becomes b2, and we again check the size condition. Unfortunately here, mu21 has a magnitude greater than 0.5, so the size condition is not satisfied. Thus we update b2 by taking the old value of b2 and subtracting off the rounded value of mu21 multiplied by the basis vector b1. We plug in all of the appropriate values, and then we arrive at b2 being updated to the vector 4, 5, 4. Now we check the size condition yet again, and we see that mu20 has a magnitude that also fails the size condition. However, here we have something that we did not have in the two-dimensional case. We have checked the size condition twice in a row. This is because, unlike in the 2D example, we have enough basis vectors to make the for loop in our algorithm non-trivial. We update the value of b2 in the same manner as before. This yields b2 being updated to the vector 0, 1, 0. From here, we check the Lovasz condition yet again. This time, we do not satisfy the Lovasz condition, so we must swap the vectors b1 and b2. We update our Gram-Schmidt vectors, and we also set k equal to 1. We hop into another loop through our algorithm, find that we satisfy the size condition here. From here, we check the Lovasz condition again, and we see in this instance we have not satisfied the Lovasz condition. We see that, as before, we need to swap the current working vector with the previous vector, meaning we need to swap the vectors b1 and b0. However, this particular swap is more interesting than the previous swaps. The vector 0, 1, 0 was once in the place of b2, and has since trickled down all the way to b0 through successive swaps. Because we have now changed our basis, we again update the Gram-Schmidt vectors to be to their most current form. We again check and fail the size condition, so we update b1 by subtracting off the appropriate vector multiplied by mu10. Let us recall that an LLL reduced basis should be nearly orthogonal, but interestingly here we have the vectors b0 and b1 are actually orthogonal, and we also have the vectors b0 and b2 are actually orthogonal in this current state. We are not quite at an LLL reduced basis just yet, but this is a good step in the right direction. We check the Lovasz condition. It is satisfied, so we may increment k. Our working vector becomes b2, and we find ourselves with quite literally an edge case of the size condition, as mu21 has a magnitude of exactly 1/2. However, this is no issue because this is not a strict inequality. Just a few seconds later, we find ourselves with an edge case in the other direction. We find that mu20 is 0, and this is because the vectors b2 and b0 star are orthogonal. We check the Lovasz condition one more time, and we find that it is satisfied. So now we may increment k one last time, giving ourselves 3 total vectors in our provisional basis, meaning we have a complete basis for our rank 3 lattice. We now turn our attention toward some of the applications of the LLL algorithm. The first such application that we will go over relates to the approximation of algebraic numbers. Let's play a game. Pretend for a second that you do not know that the square root of 2 has the decimal expansion that appears on your screen. Instead, I will hand you this decimal expansion and tell you that this is the approximation of some algebraic number. I want you to go and find me the minimal polynomial of this algebraic number. But because I want to make your life more difficult, and because we live in the real world, I'm not going to give you the entire infinitely long decimal expansion. I'm going to hand you some finite number of these digits, and you're going to run, and you're going to find me the minimal polynomial. Good luck. Here are 6 of the digits. Hopefully that will be enough. Where may you even begin to solve this problem? Well, first, let's set a target for you. Your goal is to find some polynomial with integer coefficients such that f of alpha is small. Leveraging the continuity of polynomials and the fact that alpha is very close to your target algebraic number, in this case the square root of 2, if f of alpha is small, then there's a good chance that f of the target algebraic number is 0. If you cleverly choose the degrees of the polynomials that you look at, you can use this process to find the minimal polynomial of the square root of 2, or whatever algebraic number you happen to have an approximation of. To do this, consider the lattice spanned by the columns of this matrix. We construct this matrix by taking the identity matrix and appending the row 10 to the 6, the floor of 10 to the 6 times alpha, and the floor of 10 to the 6 times alpha squared. However, we won't always use 10 to the 6 when doing a process like this. For instance, if you knew, say, 9 digits of your algebraic number, you would want to use 10 to the 9th. Additionally, the size of this matrix encodes the degrees of candidate polynomials. The maximum degree of a candidate polynomial is the number of columns in this matrix subtracted by 1. That is, because I used a 4 by 3 matrix here, I am guessing that the algebraic number in question here, the square root of 2, has degree no more than 2. So we've set up this matrix. Now let's see how we will use it. First, let's just substitute in these actual values. The columns of this matrix make up a basis for a lattice. So we may apply the LLL algorithm to this basis, and then we may replace this matrix with the matrix made up of columns being this LLL reduced basis. For our purposes, we really only care about the shortest vector in this LLL reduced basis. That is, we really only care about the first column of the matrix that you see. What is the significance of this vector? Well, it encodes the polynomial that we hope is the minimal polynomial of the square root of 2. Each entry corresponds to a different degree term in the polynomial, and then we just throw out the last entry of this vector. If we read off the polynomial encoded by this particular vector, we find the polynomial x squared minus 2. This is exactly what we wanted. We got the true minimal polynomial for the square root of 2 just by using an approximation for it of only 6 digits via the LLL algorithm. Maybe the last example was a little bit too easy. Other than choosing a rational number, the square root of 2 is the simplest algebraic number that we could have done this process with. So let's crank it up a bit by picking a more complicated number, such as 17 to the power of 2/5. Again, here is a 6-digit approximation of the decimal expansion. We will guess that this number is degree 5 or less, giving us a bigger matrix, and I'll just jump straight to the LLL reduced version because there's too many numbers to really keep track of. Let's throw out all those garbage columns and cut straight to the meat and potatoes. The shortest vector in the reduced basis. Again, we read this off as encoding a polynomial, but now it encodes a degree 5 polynomial. Let's read off the polynomial this encodes. There it is, the minimal polynomial of 17 to the 2/5. Hold on. That's not the minimal polynomial to 17 to the 2/5. By design, we can pretty much read off the minimal polynomial of 17 to the 2/5 as x to the 5th minus 17 squared. So where did we go wrong? We weren't precise enough. We just need to throw more digits at it until it works. How many will it take? After trying out a total of 15 digits of precision, we finally have this algorithm produce the correct minimal polynomial. I could not find any documentation on this, but I suspect that given any problem like this, if you throw sufficiently many digits at this, you will eventually come up with the correct minimal polynomial. Although in practice, when doing this, you may run into something like floating point precision errors, like I did when testing out some of this functionality. This process of approximating algebraic numbers is only one example of how the LLL algorithm can be used to find integer relations between different numbers. There are also other applications of integer relation problems. For example, factoring polynomials of very high degree can be done relatively quickly via lattice basis reduction like this. And Diophantine approximation can also be done relatively efficiently with the LLL algorithm, and this is of great interest in something, say, like algebraic number theory. We now look at yet another application of the LLL algorithm. Suppose that Snoopy and Woodstock want to talk trash behind Charlie Brown's back, but they don't want to go in private to make this communication. How can we make it so Snoopy and Woodstock can communicate publicly but have their message be secret? For this, we use public key cryptography. LLL can be used in the analysis of certain lattice-based crypto systems. We will take a detour through the description of one of these lattice-based crypto systems, in particular the N-true algorithm, which was developed by Hofstein, Pfeiffer, and Silverman in '96. Suppose that Woodstock wants to be able to receive messages under this system. He must first declare a public set of information. The first piece of this public information are parameters n, p, and q, such that n is prime, p is less than q, and the GCD of p and q is 1. Woodstock also retains pieces of private information that he will use to construct both the public and private keys. The first pieces of this private information are polynomials f and g that Woodstock generates at random. F and g live in the ring R adjoin x mod x to the n minus 1. However, instead of the usual multiplication of polynomials, in this ring we use convolution. But we're not going to get too hung up on that for this presentation because we're not getting too lost in the weeds of actually calculating these. F and g must also have coefficients plus or minus 1 or 0, and f must be invertible both mod p and mod q. If f is not invertible in either one of these, we simply keep generating polynomials f until this is satisfied. The polynomials f and g comprise Woodstock's private key, enabling only him to read these messages. We now use all of the parameters we've established so far to generate the public key, which is equal to p times f sub p times g mod q, where f sub p is simply f mod p. Snoopy now has all of the information he needs to ensure that his secret message is securely delivered to Woodstock. Snoopy prepares his secret message M for encryption, which will then be sent to Woodstock so he may decrypt it and read the message M. At this point, you might be wondering why the message M is a polynomial. If Snoopy wanted to send over the message, "Hey, don't you think Charlie Brown smells bad today?" he should just send those words, right? Not a polynomial. To account for this apparent discrepancy, we take Snoopy's message and encode it as a sequence in binary or ternary that we then convert to the sequence of coefficients for the polynomial m. In this way, the data of Snoopy's words and the data of the polynomial m are equivalent. Snoopy also calculates a random polynomial r that will be used in the encryption and decryption processes. Snoopy now uses his message m, the polynomial r, and the public key h to generate his encrypted message e. Remember that the message is now locked away, and we cannot read it without using Woodstock's private key. Snoopy now sends this message over to Woodstock, and Woodstock can begin the process of trying to read it. He applies a few calculations involving the encrypted message E and his private key. This leads him to finding the value of M, the message that Snoopy intended for him. I'm glossing over the details a little bit here, but all of the constraints that we put on our parameters earlier are what guarantees that this value is equal to M. So we complete the process of Snoopy sending a secret message to Woodstock. We have now described the N-true algorithm, one particular example of a public key crypto system. We can say something a little bit stronger about the N-true system as well. All of these modular arithmetic calculations that we did in this process boil down to operations in a lattice. Crypto systems like this are appropriately named lattice-based crypto systems, and N-true is not the only example of this. Other examples include knapsack crypto systems and RSA with certain settings. And because these involve lattices, we can use the LLL algorithm to weaken these crypto systems. To fully recover the private keys given the public key, in these lattice-based systems, we usually need to solve either the shortest vector problem or the closest vector problem, or maybe the approximate variations of these questions. A lattice basis reduction attack, such as one performed by LLL, has a decent chance of solving these approximate shortest vector problems, or reducing the search space for these private keys, thus making this encryption scheme weaker. We will now move on to the last application of the LLL algorithm that I will be showing you, the Mertens conjecture. Here we define the Mobius function by case distinction. For input 1, the Mobius function outputs 1. For input of a square free number, the output is -1 to the number of prime divisors. And for a non-square free number, it outputs 0. We now use the Mobius function to define the Mertens function. For a given positive integer n, the Mertens function of n is the sum of mu k, where k runs over all positive integers less than or equal to n. We can then extend the Mertens function to the reals in a pretty easy way by defining m of x to be m of the floor of x. We now come upon the Mertens conjecture. This is the claim that the magnitude of m of x is always less than the square root of x. Even though today Mertens is the namesake of this claim, this was first conjectured by Stieltjes in 1885 in a letter to Hermite. Then in 1897, Mertens comes along and investigates this claim much more thoroughly than Stieltjes. By hand, in 1897, Mertens calculates the value of m of n all the way up to 10,000. Mertens finds much numerical evidence for his claim. It looks like the square root of x is a very good bound for the Mertens function. To illustrate this, let's look at the Mertens function all the way up to 10 million. This was much easier to do with a computer. Here's the Mertens function, and when we look at the square root, we see that it's still a very loose bound on this function. This numerical evidence could lead us to some very deep implications. As it turns out, the Mertens function is very closely linked to the Riemann zeta function. To establish this link, we begin with the Dirichlet series for the reciprocal of the Riemann zeta function and see that it's described in terms of the Mobius function mu. Because the Mobius function is very closely linked to the Mertens function, we can exploit this expression to reach an expression involving zeta and the Mertens function. Glossing over a fair bit of complex analysis, we arrive at the following integral. Because of this expression, we find that if the Mertens conjecture is true, then so is the Riemann hypothesis. This is awesome. We have the Riemann hypothesis, probably the biggest unsolved problem in mathematics, and we have all of this numerical evidence to back it up. Things are looking good. We seem like we have a route to the Riemann hypothesis. What could go wrong? Well, it looks like a lot can go wrong. The Mertens conjecture isn't even true. At one point in the process, the Mertens conjecture relies on a particular Diophantine approximation, an integer relation, something the LLL algorithm is perfectly suited for. The algorithm hits the scene in 1982, and just 3 years later, Odisco and Turril use it to disprove the long-standing Mertens conjecture. They were able to put just good enough bounds on the lim sup and lim inf of mn over the square root of n. This is pretty insane. I mean, you just saw the graph a minute ago. We checked this all the way up to 10 million and everything looked just fine. Their proof was also non-constructive, so we don't even have a particular counterexample of where this goes wrong. And it turns out the bounds and where a counterexample lies are huge. Maybe this is fine. We don't need to panic just yet. I mean, their bound barely ekes by, -1.009. Why don't we just throw a scalar multiple on the Mertens conjecture and try again? Luckily for us, these more generalized claims would still imply the Riemann hypothesis, so we haven't necessarily shut the door to a proof just yet, although it does look pretty unlikely. Just by throwing more computation at these generalized conjectures, we are likely to find similar disproofs. Unfortunately, we're not proving the Riemann hypothesis and winning $1 million today. However, we were able to see some of the strength of the LLL algorithm. Thank you for watching.